Hi, my name is Aiden Chilcutt, and my group and I decided to research the history of the universe. So the history of the universe can be divided into three distinct time periods. You have the Big Bang Theory and the first 3 minutes to the 1,000 million years, and then we can take a look at present day and future possibilities. So where did it all begin? Well, the Big Bang Theory is our leading explanation about how the universe began, but why can't we look with 100% certainty what happened at the very beginning? This is because all of the energy in our universe right now was once condensed into the size of roughly an atom. And so when you have a large amount of energy like that in such a small space, our laws of physics fail us. And so that's why we have these other possible theories such as the internal inflation theory, the oscillating universe theory. Both of these aren't as popular, but they're both very interesting on their own. And so we can better describe the universe from 10 to the negative 43 to 10 to the negative 2 seconds old. And so we first have this large, massive inflation period, followed by a radiation period where the universe was purely energy in the form of radiation to about 10 to the negative 6 seconds. We then have protons and neutrons forming from this radiation from 10 to the negative 6 to 10 to the negative 2 seconds. And you can see this on the diagram to the right. We have radiation in the form of gamma rays colliding and forming an electron and positron. And so now we have this soup of matter and radiation in the universe. So next, from about 0.01 to 1 second, all the particles are rapidly colliding in the universe. At this point, the temperature is no longer high enough to produce neutrons or protons, but it is high enough to produce electrons and positrons. It is still too hot for the nuclei of atoms to form, so no elements yet, but we also could have some subatomic particles forming that could be dark matter later on. At 1 second old, the density of the universe is very low. And at 3 minutes the temperature had fallen to around 900 million Kelvin. And at this temperature the protons and neutrons could finally come together. And so atomic nuclei are formed, and the first one is deuterium, a single proton and neutron that sometimes lasted long enough to form helium, and sometimes this helium would go on to form lithium. And so now we have a couple fundamental building blocks of the universe. And so these diagrams on the right, the top right one, this shows the temperature slowly decreasing as time goes on in the universe, and this bottom right one shows that massive inflation period right after the Big Bang.
After the fusion of helium and lithium completed, the universe resembled the interior of a star in some ways for a few hundred of thousand years. This is because it remained hot and opaque, with the radiation being scattered from one particle to another. However, once the temperature was low enough, about 3,000 Kelvin, the electrons and nuclei began to form stable atoms of hydrogen and helium, which then led to the last radiation from this period being emitted. The last radiation from this period is what is around today and what we have detected in the picture below, and is called cosmic microwave background, or sometimes cosmic background radiation. After the cosmic microwave background, the universe then entered its dark ages. It was a period of complete darkness and is believed to have been mainly dark matter. This period lasted for a few 100 million years. During this time, stars started to form and would eventually light up the universe. In the picture to the right is a picture of the first light after the universe's dark ages. And at around 400 million years, the universe started to reionize, which is called the cosmic reionization, where the stars, galaxies, and quasars emitted UV light that stripped electrons from protons and started to ionize the intergalactic medium.
Hello everyone, my name is Caden Russell, and today I'd like to talk to you about the present day onward. For the past billions of years, the universe was dominated by galaxies and stars, but that is no more. We are now in a dark energy dominated era. So dark energy composes almost 68% of the universe, and it is what causes the expansion of the universe. Between galaxies, gravity is too weak to overcome this expansion, but inside galaxies, gravity can counteract it. And the future rate of expansion due to dark energy will determine one of the many paths that our universe will go down. One such is the Big Rip. Dark energy continues to accelerate the expansion of the universe. This expansion grows until gravity can't compensate. Galaxies are torn apart, then stars, and eventually all forces are overpowered as the universe expands faster than light and there can be no particle interactions. We're left with a universe of empty particles that are unable to interact with each other. A sad fate. Another way that could happen is the universe continues expanding, but not as fast. Galaxies continue expanding and stars get further and further away from each other. Star formation stops at around 1 trillion years, and the last stars run out of fuel at around 120 trillion years. Only black holes remain, but not for long, as they decay away due to Hawking radiation. So 2 things might happen if subatomic particles do not decay or do decay. One thing is, if they do not decay, iron stars may be created. They're theoretical stars made of pure iron, and they're created due to cold fusion of hydrogen atoms due to quantum tunneling after an immense amount of time. Alright, this is our works cited, and that has been our presentation.